Hello, my name is Michael Bartczak, a college undergraduate studying the major of electrical mechanical engineering technology, and today I will be demonstrating how to simulate Lab 10 pick and place in ABB RobotStudio. I will begin by creating a new file to walk through the setup process of all of the mechanisms, sensors, and station logics, then proceeding to a readied solution to explain the final code. So to get started, we will want to select Solution with Station and Virtual Controller. It may be named as you wish and saved to any directory you wish. All of these options should be left as default, and then we're going to create the station and wait for the controller to start up. Once the controller is almost done setting itself up, we will be prompted to import a library. I will be using the first one offered. Now that our robot has finished being set up, we can fetch the end effector we will be using. For that, go to Import Library, Equipment, Tools, ABB Smart Gripper. Simply click, leave as default, and now that the mechanism is in the station, click and drag onto the robot mechanism, and verify to update its position. It is now attached to the robot. We will do two more things. We will synchronize the station with Rapid and make sure that specifically the tool data and servo are selected for synchronizing. This will send the tool frame of the servo to the flex pendant for later use. Additionally, we will want to modify the mechanism of the servo, add a new pose, set it as open gripper, and modify its joint values. This will control how much it can slide. Within the mechanism, we want it to be fully open. And OK, we will also leave it in that pose. Now that we have finished setting up our gripper/servo, we can proceed with setting up the station logic. To find that, you will go to Simulation, Station Logic. Within Station Logic is where objects such as sensors and events such as attaching and detaching are housed and actuated using signals sent by the controller. So to get started, we will create a line sensor, and we will then go back to the view and see that it has been created here. I will quickly edit the height of the sensor to be about 25 millimeters and a radius of 10. I would also recommend setting up the dimensions of your sensor before attaching it to the TCP of the gripper. Additionally, before proceeding, make sure that it is active. Now that that is done, you can right-click, attach to, servo gripper fingers, update its position, and it will attach to the TCP. Additionally, should you desire it, you can make the sensor invisible for aesthetic purposes. Now that that is done, we want to create some events associated with the sensor. Those being attach and detach. These will be used to actually pick up and place the peg for the actual pick and place operation. Now, note that these have to be wired together. Specifically, sensed part needs to go to child of attacher, and child of attacher needs to go to child detacher. And once that is all set up, we now need to actually create the signals that'll actuate attacher and detacher. For that, we will go to Controller, Configuration, I/O System, Signal, and right-click to create new signals. We will name the first one Attach, and make sure that you set these to outputs, specifically digital outputs. And once that is done, can leave everything as default and repeat for detach. Furthermore, for these changes to take effect, you will have to restart the controller. Simply hit that restart button. And you're ready to go. Now we can go back to station logic, add the attach and detach signals, and wire them so that attaching executes the attacher and detaching executes the detacher. Additionally, we will want to set the parent of the attacher as being the robot, otherwise it will not function correctly. Now that we have finished setting up our basic station logic, we can return to View 1, Home, and begin importing some of the objects we will be working with in the lab. Go to Import Geometry, and select the files. Make sure that they are saved to an appropriate type, such as STL, before proceeding. Double-click, and it will import them to the solution. We can then right-click Position, Set Position, to move them about in the solution and reorientate them. I will now import the next object, one instance of peg, move it over here, reorientate, and now that that is done, I will quickly jog the robot so the end effector is hovering over the peg, and we will begin using the modify mechanism as seen before to limit how much these open and close to make it look a bit more natural. Now that I've gotten the gripper into position, we will edit its poses once again by going to modify mechanism, and at this point you would like to edit the open pose to not be at the maximum width, but rather just barely cusping the peg, or just about to cusp the peg. And we'll add another pose to represent grabbing the peg. That looks, I believe, good. That'll do. Make sure that the transition between them is not too extreme. Now, we need to add some commands to our station logic so that those poses actually swap in response to the attacher and detacher signals being sent. To do that, we're going to go to station logic, right-click, manipulators, pose mover. We will want 2. And once you have them, I would recommend double-clicking, set the mechanism to Smart Gripper, and then set it, pardon me, to Open Pose and Closed Pose. As such. And then I will use the same signals to actuate them. Pardon me. There we go. When it attaches, wire these to execute, or whichever signal you wish to use. And now those poses will also be triggered in response to the attach and detach signals being sent. And with that said, we have officially concluded the setup portion. I will now return shortly with the code portion. To take care of some additional groundskeeping before we proceed, some options you may find useful before actually getting started with the lab, go to right-click on your gripper and make it not detectable by sensors, and likewise do the same under Modify for each of these palettes. This will help prevent any issues with the gripper detecting and trying to attach to itself, since in pretty much both the open and closed poses, the line sensor intersects with it slightly, And likewise, we don't want to accidentally pick up the palette. Furthermore, regarding how line sensors work, they sense objects through intersection, which is to say they notice some part is physically jutting into their volume and crossing over. The reason why I bring this up is because sometimes it's possible to render parts as being hollow to help save on computing power. It's basically just be more efficient. That might cause issues with sensors not being able to detect them if they're, say, fully enclosed within a part. Say if this was considerably thinner and all the way in the part, it might not register it. So just keep in mind and make sure that either the radius is wide enough or there's some amount of protrusion from the part you're trying to pick up to properly sense it. Just a quick addendum, as I forgot to mention this before. Earlier in the video I asked you to synchronize the station to rapid and never really explained the reason why. It's because if I pull up the flex pendant now, the library for the gripper that I used had a predefined TCP and tool frame. And if I could set it into manual mode, by synchronizing the station with rapid, it'll import that tool data onto your flex pendant. That is all. Now, looking at the setup, most of you have probably already figured out what Lab 10 is specifically. Effectively, we have 2 pegboards and a singular peg. Starting from a position A1, move it between these boards, offsetting its position by 1 hole each time until eventually you have gone through the entire board, going up each row and ending at A9 and B9. Now, let's discuss how I actually solved this. So, the first thing we're going to want to pay attention to is the fact that these 2 plates are at an angle relative to each other, and that tells us 2 things immediately. Both are going to need their own work object, and both are going to need their own robot targets for actually picking up the peg or positioning themselves right above the peg. So, the first thing we'll actually want to take care of those 2 tasks is defining the work object. So to do that, you'll want to go to Controller, ensure that you're in manual mode before proceeding, and if for whatever reason you're unable to switch between these, simply restart the controller and that problem should fix itself. Click here to bring up the flex pendant. It does have a startup time normally, however I had it open. And you will be starting in the base coordinate system. So, to get started with defining our work object, you would want to go up. I would also recommend before doing this, just quickly going to your smart gripper and then setting it to either the home or sync pose, just so that you have a nice fine point for actually tracing the edge of this work object. So now that we have everything set up as we need it, I'm going to attempt to semi-quickly get a basic work object defined. This is always a pretty difficult task to actually do well, even in a physical environment. It's usually moderately worse in software. But with a little bit of perseverance and minor amounts of collateral damage, you will get to where you need to be. So, now that we have a rough starting position, you would go to drop down, program data, work object, and then you would simply create a new one, give it a name, make sure that its scope is specifically global. That has to do more with how my code is written. So, and once you have that ready, go to Edit, Define, and we will be using the 3-point method. Note that x1 is the position of your origin, which I could make a bit better, like so. And then once you're in the spot you want to be, modify. X2 represents your x-axis. We want it going in this direction, and then the y. Also note that I will be doing this for only one board and one peg. Do keep in mind that you have to define the other one to complete the slab correctly. So that's X. Now I will zoom over to Y. And we're done. That has given us a defined work object. You can test if it's defined correctly by simply going over to the jogging menu, making sure you're in the work object. This time it is quite important, selecting your frame and then see when you go in the X, do you go across the board? Yes. You're looking for nice smooth motion. And that tells us we did it well. So now that we have that, we will switch over to the actual plate A I had ready before. Make sure that it is functional. We will go back to the gripper and now open her once again. And within program data, we will now view types. You're looking for a robot target. It won't be there initially. You'll need to pick it out of the list, and the process is similar to before. I'd recommend global and constant. Any name is fine. And instead of define, we're going to modify position. And to do that, we will jog the robot over the peg. I would recommend defining the position of your robot target as being directly above or in the position you'd want to pick it up. So hovering over the pin with its jaws open. Once you're at the position you want to be, simply hit modify position. That will modify the position of point 10, and we can verify that it has been assigned correctly by going back to the jogging menu, ensuring that you are in the work object coordinate system and the one you did before. Then simply hitting go to, point 10, hold this button, and you should wind up at the target. Now, since this is only for demonstration purposes, I will only be defining it for plate A. With regards to repeating these steps for plate B, some commands you may find useful include this button here, which swaps from jogging in the X, Y, and Z to displacing or rotating the joint motors. And the reason why that might be useful specifically is for rotating the sixth joint, just so that the gripper aligns with, the axis, should you desire it to. Additionally, the align command, purpose of which is to ensure that your tool frame is perfectly perpendicular to some frame, either a work object or the world, might be beneficial to make sure that you're actually approaching the pin head on. Post-editing mic once again, just adding some further clarification. What the align tool does specifically is, if I can pull it up, is it will ensure that the z-axis of your tool frame is parallel to the z-axis of your world frame, or whichever you select from this drop-down. Which is, and what I meant to imply by saying perpendicular was that your tool will be perfectly perpendicular to the workspace as such. With all of that finally said and done, we can start talking about the main code used to have the robot pick up and move the pin around. So to access our code, you can do it via the flex pendant, but I don't recommend that as it's difficult to read. Rapid. You'll have a rapid drop down here. click it, follow it to main, and double click. Now let's walk through this sequentially. So in order, before our main procedure, we have our variable declarations, and just to quickly go through what the purpose of each one is. Delay time is more so related to doing the lab physically, which we had to do before simulating it, and it's mainly important when dealing with a physical gripper since there's a delay between the actual gripper shutting and when you sent the signal to tell it to close, so it's about half a second. X and Y increment, that just tells you how far in the X and Y direction each hole is from each other, specifically the center point. We will be using those to offset our initial pick point in the X and Y direction as we move up through the board. Safety Z offset is effectively 150 millimeters above the pick point, and its purpose is just to make sure that before directly attempting to pick up the peg, we are approaching from a position straight above it, going down to make sure that we don't accidentally crash into the side of our peg. X and Y pause are containers just storing the present value or the present position of the peg on the board. Change W is an interesting one, mainly just because it's more of a vestigial line of code, and its original purpose was for a procedure that made use of alternating plate A's and B's, which is to say there were a bunch of move commands and it would swap whether or not that move command was meant to be done in plate A or B. That solution wound up not being as fruitful as I wanted, and presently its only real purpose is just to make sure the pick and place procedure works correctly, since procedures have a bit of a quirk where they don't quite want to work right or throw errors if they aren't getting past at least one variable. And we obviously know what work object and robot targets are. So going into the main procedure, in order, on startup, you're going to wait some time before moving, and then additionally, we're going to use a pulse command. In reality, you would be using set and reset to actuate your gripper. However, here, we'll be using pulse do, which effectively just sends 1 through whichever signal we're specifying here. So in this case, we're telling to send 1 via the output detach. And that's done just to make sure that if there is presently anything in the gripper, or more importantly, if the gripper is closed starting out, then we open it before we crash into a peg. So then we're going to go into 2 for loops, the purpose of which, if you're familiar with other coding classes, you've probably seen this example. 2-dimensional arrays. Using 2 loops like this, it's rather convenient to just go through in order the contents of a 2x2 array, which, looking at this scenario, it's a good way to think about these pegs as a 3x3 2D array. So what these loops are going to do is, in 3 iterations from 0 to 2, so start by going to 0, 0, and then taking that to the pick and place, because we're starting with these values, executing here, and then exiting, updating the current X position by adding X increment to it, and then repeating this until 3 iterations have been completed, exiting the loop, updating the current position of Y and resetting X, and then once it's all finished, return to 0, 0. Now, let's go over what the procedure itself does. In order, we're going to move J, which is a joint movement. It tends to be a bit more computationally efficient to use joint moves for when you don't need a high amount of precision. That's why I chose it. Offset, that just allows you to offset some known robot target by, an X, Y, and Z factor. In this case, all points are being offset by whatever x and y pos currently is equal to. And in this instance, we want to start above the peg before we go down. And then we always use the gripper, which for context, that's what I renamed the servo, just because it was already the gripper in my previous code. And we start in plate A. Next, we're going to go straight down onto the peg to get ready to pick it up. Note that you do at least have to put 0 for when you don't want to offset the point in a direction. And additionally, we use the find termination type for any move commands that precede a pulse. Since by using a zone, I found that a common issue was the gripper would actuate before actually reaching the robot target, just because, well, that's the purpose of a zone. It calculates some minimal accepted distance to consider the command, done, and then move on. So obviously, if you have things that are time sensitive, like attach and detach, you need it to actually reach the exact point and stop. Next, we are going to first detach the peg or anything in the grip, we are first going to do a pulse detach with our gripper, and the reason for that is a quirk of how I've chosen to write this. As you have noticed, this procedure is written in such a way that it doesn't actually need to alternate work objects in order to function correctly, and I'll explain more about what that does when we reach the end of this. Just know that for now, it is crucial that we detach, wait, and then attach before moving away from the pick position of A back to the safety point, or the safety offset. Then we will repeat the same steps, only now moving in the plate B. So we'll detach, put it down, detach, move back, and then pick it up again. And then finally, you'll notice we end with the robot holding the peg in point B, meaning that when we loop and have our x position incremented, when we move to plate A, we will already have the peg held within the gripper of the robot, which is why we can get away with not alternating these work objects, since it always ends with the peg in its hand. Now, with that concluded, let me show you what that actually looks like functioning. I will note you may be tempted to, say, use, if I can find it, the program editor and debugging to run your code. That will not work in this instance, and it has to do with the quirk of how sensors work in Rapid. Mainly, they don't constantly function in real time, from what I've seen. You do specifically need to go to simulation, simulate, or press play in order for things like sensors to actually, in real time as it's intersecting with this peg, detect that it's there and function. So, with all that said, let us simulate and see the final result. And with that, this tutorial is concluded. I hope you learned something from it.